we are going to have a look at the different groups and general tendencies within groups. Remember when we did SPD notation, we can differentiate S block elements, P block elements, D and F block elements. All right. The group of metals on this periodic table that are printed dark green in color are commonly known as the transition metals. And we'll have a look at the properties of metals when we get there. Those are the lanthanides and actinides. We don't normally work with them except for uranium that is used as a fuel in nuclear power reactors. I think I did, yes. Okay. All right. If you look in your textbooks there on page 40, you will see there are the first few bulleted points. They say group 1 and 2 metals are called alkali metals. Group 1 is the alkali metals. So group 1 is group 2 is known as the alkali earth. Metals. We don't bother with the names of the group 3s and the group 4 elements and the group 5 elements, group 6 elements. Group 7 elements are known as the halogens, and then just remember what is a halide. Yes, it's in the compound form. Okay, usually the ionic halogen. Okay. They talk about the transition metals that lie between group 2 and group 3. They form a unique group of metals, slightly different from those of group 1 and 2. Remember, metals are shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. And then we find that the difference between the group 1 and 2 metals, they are less dense, they are fairly light metals, and they are fairly soft metals. Group 1 and 2 metals are less dense, they are soft. Many of them float on water. They are soft, so they aren't high, they don't have high densities. Okay? We find that the transition metals, they usually form colored compounds, and they usually have higher densities with higher melting and boiling points. All right. Remember, the boiling point and melting point of mercury will not fit the pattern because it's a liquid at room temperature. Okay, I don't want to say more about the metals at this point. Then they say the group of metals on the right of the transition metals, these are called the B metals. On this periodic table, they're in light blue. We won't bother much with B metals, why they are called that or whatever. It's just take note, that's why they've got it colored in blue on that periodic table. Then the group of B metals, just B, capital letter B, B metals. Then the group of non-metals on the right of the periodic table, remember, there is a step going down through the periodic table. Below the step we have metals, above the step we have non-metals. In actual fact, the non-metals are only a few elements. Most of the elements are metals. And yes. Calcium is a metal. Remember, what confuses you is calcium carbonate or calcium salts. That is what your bones are made from. But it needs calcium. But you don't have calcium as a metal in your bone. You have calcium in the form of a salt in your bones and teeth. That's... It's a compound in your... Yes, yes, yes. Okay. So say properties change. Yeah, yeah. Yeah. Yes. Yeah. Yeah. Yeah, it's only a few that are non-metals. All right. If we go and have a look at the step, then we find that the elements lying on the step, like boron and aluminium, aluminium silicon, silicon germanium, germanium arsenic, arsenic antimony, tellurium, polonium, astatine, they very often have got properties that are slightly more vague. They aren't definite metals or definite non-metal properties. Carbon is one of them. It touches the step on the corner. Carbon, one of its crystalline structures in the form of graphite, does conduct electricity, while in general non-metals do not. Then we get silicon and germanium. Silicon is a non-metal, germanium is a metal, but they are both semi-conducting materials. Do you understand? Now, those elements, we call them metalloids.
Should we know each one's...
No, we will do specific things. This is just in general. You need to know the term metalloids. If I ask you what is a metalloid, then it's an element that lies on or near the step that shows properties of both metals and non-metals. Okay. In general, when we classify something, if it has mostly metallic properties, then we will classify it as a metal. But for example, tin, we get one of the crystalline structures of tin that looks like not a metal at all. It looks like a non-metal.
Oh,
All right.
So there's an
Yeah. Yes, both sides, up and down. The ones that touch the step. All right. Yeah.
So we just say on or near of head touch?
On or near the step. It's fine. All right. Now, the next part in your textbooks, they refer to group 1 and group 2, the alkali and the alkali earth metals. People, a couple of things that we need to know. When they form salts, they are usually white salts, colorless compounds. Okay? What is the properties of the transition metals? They form colored compounds because copper salts are blue, zinc is white, iron salts are red or green, etc. Okay. They are mostly the group 1 and 2 metals when they form salts. Those salts are usually soluble in water. All right. And we find that the reactivity of the group 1 metals increases from top to bottom. Group 2 also increases from top to bottom.
So the honors, this is
More reactive, yes. We don't work with them. It is just elements that there is, but many of them are made in laboratories. They exist for a short period of time because they're radioactive and they disintegrate or they break down, undergo decay. They don't make uranium, they mine it, but some of the others. Yeah, they enrich uranium to get a specific isotope of uranium that they need for nuclear reactions and stuff like that. Okay. Yeah, we don't need to know them. Just leave it, please. Okay. The transition metals then, in the next section, if you check there, they say the metals are not as dense as the well-known ones. So group 1 and 2 metals are not as dense as the well-known ones. So then the transition metals, just in general, they form a block of metals. They are hard, they are strong. They usually have high densities, hard, strong, dense materials. They form colored compounds. And then they say the metals become less reactive from left to right. So the transition metals that lie on the left-hand side of the block of transition metals, they are slightly more reactive than those that lie on the right. But it's not like a fixed golden rule. Okay. But if you do look, you'll see elements like silver and gold and platinum. They lie here on the right-hand side. Okay. And iron that we know will rust, for example, lies more to the left-hand side of the periodic table. That's just general sort of tendencies. The whole periodic table, as you work, except for the group 8 elements, we find then that group 7 and group 1 are fairly reactive. Group 2 is less reactive than group 1, so group 6 is less reactive than group 7. So there's a general tendencies of the yes, yes. Okay. Then
it has to do with electrons in the outer shell.
Yeah, mostly.
Is it that the same way with the transition metals as well?
Yes, well, not from inside out, but from left to right.
Yes, yes.
All right. The transition metals then, just very simply, this means that the least reactive ones, such as gold, are found on the bottom right over there. So the reactivity decreases from left to right and from top to bottom.
Okay, now
All right.
mercury.
Yeah.
But gold is more reactive than
Yeah, but
mercury
that's just
in those
general
solids.
tendencies. It's just it's inherent properties of the elements. Okay, so the B metals, they are very often, I put in brackets there the metalloids because they all touch the step, not all of them, but most of them do, all right? So we don't worry too much about the B metals. They just say, yeah,
Bromine and silicon and those can also be classified as a metalloid.
no, not bromine, silicon, boron, yes.
Yeah, because it also touches the
Yeah.
step. So metalloid is touching the step. It doesn't need to be a metal to.
Okay. The non-metals on the right-hand side above the step, well, we know they are dull, they are not shiny, they are not workable. The non-metals, you should know hydrogen, nitrogen, oxygen, fluorine, chlorine are gases together with group 8. That's nothing new, all right? You need to know that in the non-metals there are some diatomic elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, or diatomic, astatine as well, but we don't work with it very much, all right? So the non-metals, they have one thing in common, and that is that they are non-metals. When they bond with each other, they form covalent bonds. When they bond with the metals, they form ionic bonds. Just general tendencies. No? Then the group 8 elements, the noble gases or inert gases, helium, neon, argon, krypton, xenon, radon, they are unreactive. They have filled outer shells, so they don't react. We use them in places where we need inert atmospheres. Yeah, for example, within a light bulb. I watched a YouTube video the other day where they switch on a light bulb. They've broken the glass around the bulb and they switch it on. It burns for 2 seconds and it goes out because of the oxygen in the air. And the inert atmosphere prevents the metal from oxidizing. Now, it's not melting, it oxidizes, it rusts, and then it becomes brittle and it breaks. Okay, and it doesn't conduct as well. So, yeah. Yeah. Yeah, it will stop working, yes. All right. They work slightly different to the filament light bulbs. Okay. Yeah. All right. Then the lanthanides and the actinides, you can just put a bracket around it. We don't do anything. Just know uranium is the most important one because it's used as fuel in power reactors, etc. And it's mined in Namibia. When we do the extraction processes, we'll have a look at uranium again. Then they go and specifically look at group 1, the alkali metals. In other words, lithium, sodium, potassium, rubidium, cesium, francium. And we find that their boiling points decrease. The bottom ones are, if it's a hot day, liquids at room temperature. All right. Their melting and boiling points decrease as we go down. Their densities tend to increase as you go down the group. Just general group 1 metals. Okay? The alkali metals. Cesium is classified as a solid, but if it's warm enough, room temperature, melting point is around about 24. Here by us it will usually be in the form of a liquid. You don't need to go and remember melting and boiling points. It's just general tendencies that you must know of. Yes? Yes. Yeah. Yes. Because you require more energy to boil. Well, it's got to do with the forces. Yeah. It's just, it's inherent properties. Yeah, that's a slight discrepancy or an aberration if you want to look at it like that. No. Sometimes we find that as the extra shell is added, the nuclei are further apart, so the forces holding the particles are acting over greater distances. But sometimes it's got to do with the extra shell has an extra positive charge to it. So these things all sort of play a role. Okay, so just in general, the general tendency is for boiling points to decrease, melting points to decrease, and density to increase. Okay. The group 1 metals in general are very reactive. If I had sodium and potassium in the laboratory, I would store them under an oily liquid or within an oily liquid. The simple reason for that is sodium and potassium are so reactive that if I had them not covered by an oily substance, they will react with the oxygen and the water vapor in the air. And here by us in the summer, there's lots of water vapor in the air. The potassium will start burning. The sodium will corrode. It will become hot. There is a chance of it starting to burn depending on how much moisture there is in the atmosphere. All right. So they are very reactive. We store them under like paraffin or any oily substance. You can't store them under water because they react with water violently. So they float on the surface, they run on the surface, they melt and they burn. Okay, potassium burns with a nice purple flame. When it runs on the surface, you can see the little purple flame above it. Sodium, you cannot see that it is burning, but it melts. You can see it melts into a little droplet that runs on the surface of the water, and eventually it disappears because it forms sodium hydroxide that goes into solution. It leaves a little milky trail on the surface of the liquid. All right, we can check and see maybe if we've got some time somewhere along the line in a double period for a video on these metals. Okay. The table 3.3 in your textbooks on page 42. There they have a look at the chemical properties of the alkali metals. Now, they all react with water. If you read the first three, lithium, sodium, and potassium reacts with cold water. Sodium reacts vigorously with cold water. Potassium reacts violently with cold water. The increase in reactivity as you go down the group, they all react with cold water and they will form the hydroxide. So it will form lithium hydroxide, sodium hydroxide, potassium hydroxide. Now, if I have, let's say, sodium and it reacts with water, H2O, it is going to form sodium hydroxide. This is water soluble plus what? Yes, hydrogen gas. All right. And you would be able to catch up the hydrogen gas and you can test the hydrogen gas. How do I test hydrogen? Burning splint, whistling or popping sound. All right. So all of the group 1 metals will react similarly with water, as if it was an acid. You get a salt plus hydrogen gas. Then, if we go and have a look at their reactions with oxygen, they all react with oxygen. Yes, all sodium group 1 and 2 metal salts, most of them are soluble, so if you have to guess, you could guess them as soluble. Yeah. Okay. There are singular exceptions. I can give you the list. No. The grade 10s do the solubility rules. Yeah. All right. Then the reaction with oxygen, they will all react with oxygen. They will burn, and the product will be a white substance. So when any of these metals, let's take lithium, if lithium reacts with oxygen, it is going to form lithium oxide. Okay? Yes. And lithium oxide is a white solid. This is water soluble. Okay, but they all form white salt, so that stuff is white, that stuff is white. Okay, so that is the reaction with oxygen. They also like reacting with the group 7 elements. They are very reactive. Group 7 elements are very reactive. So let's take potassium with iodine, and it will form potassium iodide. All right, very willingly. It's actually an oxidation reduction reaction, very similar to the combustion reaction chemically. Okay. Yeah? It is the permanganate part that is the active part. You could have just as well have had sodium permanganate or whatever. Yes, but it's in the form of a salt. It's like sodium metal. It burns when exposed to air or water. But sodium hydroxide is a stable salt, or sodium chloride is a salt which is stable. Remember, the properties differ when they form compounds. Okay. So they like reacting with a group 7 elements and they form salts. The flame color, that is not part of your syllabus. The grade 10s do the flame color. Lithium is red.
Sorry, is the salt white?
Yes, they are all white salts. The flame color test, they just dip a piece of wire into the salt and they hold it in a flame, and the flame color changes depending on what metal we have. All right, so, but you don't have to worry about that. You don't do that. Lithium is red, sodium is yellow, potassium is purple. Yes, the symbol, lithium, sodium, potassium, all +1 metals because they lose their outer shell electron. And then the salts, you will see they are all white crystalline solids which are soluble in water. The sodium salts, or white crystalline solids which are soluble in water. The potassium salts, white crystalline solids which are soluble in water. Group 1 and 2 metals form white salts, and they are usually soluble. Some of the hydroxides of group 2 metals are insoluble. Okay, but in general they form soluble substances. No, you don't need to know the flame test. Then they've got there in the bottom of page 42 the reaction with a metal and water. What they go and do there in the picture is they take sodium metal and they wrap wire around it. The reason why they do that is they want the sodium to sink. If I add sodium metal to water, it's going to float on the surface. And then you cannot see the bubbles for the hydrogen gas forming. So what they're going to do is they're going to wrap a piece of sodium just in a piece of metal wire. And they put it into the water, and then you can see bubbles forming. And those bubbles are bubbles of hydrogen gas, because we said over here, when they react with water, they form hydrogen gas. Okay. The reaction of the metal with water, this is an alkaline substance. pH will be greater than 7. Okay. You can see as the sodium runs on the surface, it leaves a milky trail that sort of disappears into the water. And that is the sodium hydroxide that has been formed that dissolves. Okay. Group 1 compounds, the group 1 metals, when they form compounds with the non-metals, they are all ionic. Okay. Yeah, that's just simple. Yeah, it's just information. They say all group 1 compounds are colorless crystalline solids which are soluble in water. Okay.
Ionic.
Yeah. Soluble salts. Yes. Colorless and water soluble. The reactivity of group 1, we've already said it increases down the group. All right, then in your books they jump to group 4. Now group 4 is carbon, silicon, germanium, etc. They have in common, they actually form a unique group because the first 2 are non-metals, the last 3 are metals, but many of them are actually metalloid in their properties. In general, they have got 4 electrons in their outer shell, so depending on what they react with, they can either lose or gain 4 electrons. All right, we don't work too much with them. We will work with carbon when we do organic compounds and when we do carbon dioxide and carbon monoxide. All right. They say the central group of the periodic table shows very clearly the increase in metallic characteristics down the group. So they start off with non-metals, metalloids, metals as you go down the group. That is what that sort of sentence means. They say carbon and silicon are non-metals and tin and lead are metals, yet one form of carbon, graphite, will conduct. And tin exists in both a metallic form and a grey non-metallic form. Okay, it looks like a, well, crystalline substance. Carbon is very unique. It forms 4 covalent, or it can form 4 bonds. And this makes carbon very versatile. Okay? Depending on how much energy is available and the temperatures during which this process occurs, carbon tends to burn when it reacts with oxygen, and it forms carbon dioxide. But carbon itself also very often undergoes sublimation, and that is why when you have a flame in the laboratory and you don't set the Bunsen burner to have a blue flame, you put something on. If the flame is yellow and smoky, then it's full of carbon on the outside. This is the carbon from the hydrocarbon fuel that has undergone sublimation. It forms a single little atom of carbon, which they sort of collect together, and it condenses, or it resublimates on the surface of the object, making it all sooty and black. All right. The fact that carbon can form 4 bonds makes that it can have various shapes. We know about the different crystalline structures of carbon, diamonds and graphite. And then there's another one, they talk about fullerene, but we'll have a look at them when we get to that. They say silicon has properties of both metals and non-metals. All right? It is a gray solid that looks like a non-metal, but it conducts electricity better than a non-metal does in general. We call it a semiconductor. Now, semiconductors, the difference between a semiconductor and a normal conductor is, for a semiconductor to be able to conduct, it needs a minimum potential difference across its ends. If you have more than that, then it will conduct. But if your potential difference is less than that, then it doesn't conduct. Okay, germanium works like that. I can't remember exactly. I think it was 1.6 volt and 2 volt or something like that. Yes, if I have less than that, it does not allow charge through. But if I have more than that, it does. Okay. The group 7 elements, they jump to after that one then. The group 7 elements, we call them the halogens. They are all non-metals: fluorine, chlorine, bromine, iodine. Fluorine is a yellow gas. Chlorine is a green gas. Bromine is a red-brown liquid, and iodine is a shiny, dark purple crystal. It's almost black. All right. Iodine tends to undergo sublimation when you heat it up. It doesn't melt. Bromine is actually very poisonous. It's carcinogenic. It can cause cancer. So in general, in school laboratories, we do not work with bromine. When you do buy bromine, you can't buy a bottle full. It's usually in little glass ampules that you have to break open, and then there'll be a milliliter or 2 in the little ampule. But you need to work with it under special conditions where you have a fume cupboard. You should not breathe in the fumes of bromine. And because it is a liquid, liquids tend to evaporate. Okay, so we don't work with bromine. We will work with the salts of bromine, potassium bromide, for example, but we won't work with bromine as a liquid in the school laboratory. They say the group 7 elements, all of them are poisonous, but they are also very often micronutrients. For example, iodine. Your body needs iodine. It helps to regulate the function of the thyroid gland. But in too large amounts, it is poisonous. That is why they can chlorinate the water, because in small amounts, your body can cope with the chlorine. But in large amounts, it is poisonous. Okay. So in general, the halogens are all poisonous. Bromine especially is a carcinogen. Okay, it causes cancer. The halogens, there's a table 3.6. In general, if you go and have a look at melting point, fluorine is a gas, iodine is a solid. So what happens to melting point? Does it decrease or increase down a group? It increases, because solids have higher melting and boiling points than what gases do. All right? So general tendency, melting point increases. Boiling point also tends to increase down the group. The state at room temperature, fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. You must know that. and their colors yellow, green, brown, and purplish or almost black. The group 7 compounds, they are very reactive and they like reacting with the metals. Okay, so they form ionic compounds. And when they react with other non-metals, for example, hydrogen chloride, it forms covalent bonds. No, it forms molecular substances. Hydrogen sulfide, carbon dioxide, sulfur dioxide. These are molecular compounds, and molecular compounds have low melting and boiling points. No, they are usually in the form of gases. Single ones of them will be a solid at room temperature, and usually they also undergo sublimation if they are solids. More about the group 7 elements. They form ionic compounds. Metals are hard, they are crystalline. They contain negative ions. Typical one is sodium chloride. We talk about the halogens, and their ions are the halides, but I've repeated that so many times you should know that by now. An anion. The halogens. Fluoride, chloride, bromide, iodide. Yeah, they're all -1. They all gain 1 electron when they form ions, because they have 7 electrons in their outer shell. Most halides are soluble. Here's one of the solubility rules that you can go and learn. Fluorine, chlorine, bromine, iodine, their compounds are soluble, except silver, lead, and mercury. So mercury chloride is going to be a solid. Lead fluoride will be a solid. Okay, but all of the other salts, when they combine with the metals, and they can combine with a variety of them because they are very reactive, they will all be soluble. No? So all the halides are soluble except silver, lead, and mercury. Okay. What more? All right, that's the halides. Okay, done. Top of page 45 there, they say some halides are insoluble ones. The ones that are insoluble are silver, lead, and mercury. In general, when we test for the presence of halide ions, in other words, we don't work with fluorine that much either. Chlorine, bromine, and iodine. When we test for the presence of this in a solution, let's say I have a test tube, and in the test tube I have a little bit of potassium iodide. All right? Now, how do I go and identify the presence of chloride, bromide, or iodide? So what we go and add in with all of them, we usually add a little bit of nitric acid. That's the first step. The nitric acid simply functions to, if there are any insoluble contaminants possibly in the solution, it keeps it in solution. Then the reagent with which we test for the presence of halide ions is silver nitrate. Now, you could have actually tested with lead nitrate or mercury nitrate as well. Okay, because they will all form insoluble salts. But I think some of the others under special conditions will dissolve. So the reagent we use to test for group 7 elements is silver nitrate. Silver nitrate looks like water. All right, if you mess it on your skin, it changes your skin dark brown. It's like it reacts with the proteins in your skin. Okay. No, I think they're fairly neutral, the salts. Yeah. No, not at all. No. Okay, now what happens is, let's say I have a solution of potassium iodide and I go and add silver nitrate. We are going to get silver iodide and potassium nitrate. So we get silver iodide, and this thing is insoluble. plus potassium nitrate, and all nitrates are soluble. So this stuff will form a precipitate. Now when you do this test, well, they differentiate. They say that this one, silver chloride, they say is white. Silver bromide is cream. And silver iodide is yellow. This is the precipitate that they're talking about. Now, unfortunately, the white, the cream, and the yellow precipitate, their colors are so close together that you could maybe guess the one that is white. But if you have a precipitate, a single test tube, you cannot decide whether it is cream or yellow. So we have to go one step further to go and confirm. We now know if you get this white or cream or yellow precipitate, we know we've got one of the halides. All right? But which one? So the second part of this test is we start with dilute ammonia. Now, ammonia, when I dissolve it in water, it forms ammonium hydroxide. Okay, so I go and add dilute ammonia to my first test tube. If it is a chloride, that white precipitate becomes soluble. It disappears and you get a clear liquid. Okay. If you go and add dilute ammonia to that one and that one, the precipitate stays. So now you have separated the chloride. The next step, yes, they will be insoluble in dilute ammonia. The second step is to use concentrated ammonia. Now, when you do the test, obviously this one will become soluble because it's soluble in dilute ammonia. But you will find that this one becomes soluble in concentrated ammonia, soluble in dilute ammonia. Yes, you do it in steps. And then you will find that this last one remains insoluble. And then you have distinguished them from each other. Dilute ammonia. Do you understand? This is very important work. Okay? You need to know this. The identification of the halide ions in your textbooks. No, we don't work with that. Your syllabus just specifies chlorine, bromine, and iodine. Okay. The test for halides in your textbooks, page 45, they say the reactions of halides with silver nitrate solution, followed by some dilute ammonium hydroxide, is the standard way of distinguishing between them. In the table, they show clearly chloride is a white precipitate, bromide is a cream, iodine is a yellow precipitate. Fluoride doesn't form a precipitate. There's a different way to test for that. It's not part of your syllabus. Then they say with dilute ammonia, the precipitate, the chloride, dissolves. The other two remain insoluble. So how do we distinguish them? We use concentrated ammonia, and we will find that the bromide will become soluble and the iodide will remain insoluble. Okay, that's it. Yes. Last period we had a look at the test for chloride bromide, and iodide. Just to recap very shortly, because this is very important, we add silver nitrate. In each of them, we get a white precipitate, a cream precipitate, and a yellow. But you saw that they are very difficult to distinguish. One would probably, if you took a guess, be able to guess the white one. So there is a second step that we do to this test. We go and add dilute ammonia. It's just NH4OH, all right, dilute ammonia, and we find that this one will dissolve, the rest will stay. Then we take concentrated ammonia, and that one will dissolve, but that one won't. All right, this is an important test. Over here, they acidify with a bit of nitric acid, just for impurities that could possibly interfere with the test. Okay. Now, we are still busy with the halogens and the halide ions. The next thing is the reactivity of the group 7 elements. I have said to you, fluorine is the most reactive, iodine the least. Okay. Now, they can undergo displacement reactions. And the rule says the more reactive halogen can displace the less reactive halide from its compound. All right, now what does this mean in practice? For example, let's take fluorine, because fluorine is the most reactive one. So if I have fluorine and I have a solution, for example, of potassium iodide, we will find, if you go and look at the reactivity between fluorine and iodine, we will see fluorine is more reactive. So according to this, the more reactive halogen, that one, can displace that one, the halide. So the product that we will get would be potassium fluoride plus iodine. Yes. Okay. It's an easy one. So, eventually, what it comes down to is fluorine gas can displace chlorine from potassium chloride, bromine from potassium bromide, iodine from potassium iodide. But chlorine cannot displace fluorine from its compound. In other words, if I gave you this equation, if we said we have chlorine there and I bubble chlorine through a potassium fluoride solution, what is going to happen? Which one is more reactive? This one or that one? That one is more reactive. So can the less reactive one displace the more reactive? No, it can't. So here won't be any reaction. Yes. You say no reaction. Okay. Yes, you need to know them. All right. That is very important. So this is, yeah?
So with the non-metals over there, the reactivity increases the way you go down.
Not all of them, but specifically group 7 decreases as you go down. Okay? It depends on from group to group. Okay. So in your textbooks, they're on page 46. Oh, okay. On page 46, we have the displacement reaction they say it starts right down at the bottom of page 45. They say this reactivity shows the reaction between halogens and other halide ions. It shows that when a halogen high in the group, in other words, a reactive halogen, containing the, is added to a solution containing the ions of one lower down, in other words, less reactive, there is a reaction. For example, chlorine solution is added to sodium iodide. There's a reaction. Chlorine plus sodium iodide will give you sodium chloride plus iodine. Below it they say, this is because the chlorine is more reactive than the iodine. It competes with the iodine for the sodium ions and wins. If bromine solution is added to a solution of sodium chloride, there will be no reaction because bromine is less reactive than the chlorine. Mark off on that same page, question 3.5, 3.6. And, okay, not 3.7, 3.5 and 3.6. The next group that we look at is the group 8 elements, the inert or noble gases. Why are they inert? Why do we call them noble gases? They have filled outer shells. What does this mean? They don't have bonding places, so they can't bond. Now, it's not impossible. One can force them to react, okay? But in general, for the extent of our syllabus, they do not react. High temperature, high pressure, catalysts, etc. But it is not, it doesn't go easily, okay? So, right at the bottom, page 46, the unreactivity of the inert gases is that they have a full shell of electrons. And then just there's a table, 3.9, general properties. We find that melting and boiling points and densities increase as we go down. All right, melting and boiling point and density increases. Some of the uses of the inert gases everywhere where we need an inert atmosphere, for example, in light bulbs. They say the helium is used for filling airships and balloons. Now, historically, they used hydrogen as well. What was the problem with the hydrogen? Yes, it makes an explosive mixture when it's mixed with oxygen. All right, so the airships from the olden days, they used to be filled with hydrogen, but nowadays if you want to have an airship, it will be filled with helium, because helium is unreactive. They say it fills airships. It's used mixed with oxygen to form a gas for divers to breathe. Why? Yes, because the other elements can react. Okay? We are not designed to breathe pure oxygen. We breathe approximately 1/5 of the air that you take in contains oxygen. So when you go deep sea diving, can you suddenly start breathing pure oxygen? No. So they mix it with helium. Why with helium? It's unreactive. All right, because some of the... It's probably got to do with the availability, yes. Okay. Neon used in fluorescent lights. When an electric current is passed through neon, it gives off a bright light. Argon, filling of light bulbs, it's unreactive, so the filament does not burn away. The next group that we have to have a look at is the transition metals. Now remember we said that in terms of the properties of metals, shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity, but how do they differ from the group 1 and 2 metals? Usually the transition metals have high melting and boiling points, higher densities, and they form colored compounds. While the group 1 and 2 metals have lower densities, lower melting and boiling points, and tend to form white salts or compounds. Table 3.11, just general properties of some of the metals. There isn't a pattern that you say it decreases from left to right or from top to bottom or increases as you go. It's just very general. The they've listed scandium, titanium, vanadium. So scandium, titanium, vanadium, then chromium, manganese, iron. It is the first horizontal row of the transition elements. It's period 1, 2, 3, 4. No? Okay? Iron, cobalt, nickel, copper, and zinc. So they've just taken the first row, horizontal row. And very simply, if you go and look at melting point, it tends to decrease. Boiling point tends to decrease. And density tends to increase, although there are some discrepancies. All right. They like asking questions. They give you a list of melting and boiling points, and they say, describe the trend. Then you must go and see, is there a general increase or decrease? Yes or no? It increases or it decreases. Are there any aberrations in that list, with the exception of that one and that one? Okay, that's how you describe the trend. Yes, you don't need to remember specific values or give specific reasons on that one. Okay. On page 48, if you go down, the first sentence below the table, these metals are much more dense. And in the second paragraph, transition metals form colored compounds. And then they list a couple of the transition metal salts, and you will see they are yellow, purple, green, blue, orange, brown, red, etc. Okay, they form colored compounds. It's not that some of them don't form white salts. For example, zinc forms a white salt. Okay, but in general, they form colored compounds. In general, the transition metals are also very often used as catalysts during industrial processes. And one of the topics that we will have a look at a little bit later on is some of these industrial processes. Okay, so the catalysts then are probably transition metal elements. Uses of transition metals, because they are hard and strong, and because they are fairly unreactive in comparison, for example, to sodium and potassium and magnesium. All right? Iron doesn't start burning if you make it hot enough, but magnesium does. So relatively speaking, because of its unreactivity, strength, hardness, etc., these metals are used in industrial processes and in manufacturing when we need, for example, tools, etc. So they say transition elements are hard and strong, and they are not easily corroded. So one important use is as a catalyst. We've just done that. What does a catalyst do? How does it work? Yes, you know the little rhyme. Catalysts make reactions go faster because it lowers the activation energy needed. Okay. Table 3.13. There they're going to have a look at some industrial processes. We will have a look at ammonia, sulfuric acid, the making of those two. The catalysts are iron and vanadium and platinum and nickel and titanium, making of polythene. You must just know one or two uses. The first two, definitely, iron and vanadium, because we are going to do the Haber process and the contact process. Iron is in the manufacture of ammonia, the catalyst, and in the manufacturing of sulfuric acid, the catalyst is vanadium. Okay, I think I must stop at this point, because the next thing that we must do is the transition metal ion, the complex ions. Okay, and it's slightly different from what you've done normally. I want the whole period, because we're just going to get started and we're done on that. So at this point, I am going to stop. Yes.
A rare tropical disease, the Zika virus, is spreading rapidly in parts of Latin America and the Caribbean. In March 2015, the Zika virus first surfaced in Brazil and has infected more than 1 million people. The International Atomic Energy Agency, the IAEA, and the Food and Agricultural Organization, FAO, have responded swiftly to the Zika crisis. These UN agencies came together to make available a nuclear technology that controls pests by rendering the males infertile with radiation. This is called the Sterile Insect Technique, or SIT. A group of scientists from around the world gathered in Brazil recently to examine SIT's effectiveness. They have concluded that SIT is an efficient, safe, and environmentally friendly technique to control pests and fight diseases such as Zika. Conceived in the early 1930s, the idea behind SIT is a simple one. It involves bringing the insects into a laboratory, rearing them in large numbers, and sterilizing only the males with ionizing radiation such as gamma or X-rays. For SIT to work, millions of sterile male insects must be released into the wild for several months to outnumber the fertile ones.
What's going to happen is that the sterile males are going to seek out the virgin females, they're going to mate, but there's going to be no offspring. So there's going to be reduced population replacement, and you will see that after a while the target population is going to go down.
At the IAEA's Insect Pest Control Laboratory in Siebersdorf, Austria, entomologists have been developing and improving this technique for over 50 years. It's already been used in around 25 countries, mainly to tackle pests, such as fruit flies and tsetse flies. Experts are now developing techniques for the mass rearing of mosquitoes and transferring them to countries affected by Zika to help them integrate SIT into their pest control programs. Over 100,000 mosquitoes from 3 different species are kept here. Special attention is being given to this one, the Aedes aegypti, which is responsible for spreading the Zika virus.
What we have seen in the past is that Aedes aegypti control with conventional control tools has not been very successful. So we consider this as one additional new tool that could be used to integrate with the conventional methods.
Scientists have created a special environment for the entire life cycle of the mosquito, from the egg to the larvae, to the pupae to the adult. The pests live, feed, and mate in large, specially designed cages. Thorough research has determined the right dose of radiation to sterilize the males, without damaging them or affecting their mating ability. In a further step to help countries tackle the Zika virus, the IAEA is providing portable equipment for the rapid detection of the virus. Training scientists from the affected countries to use this system is also underway. When fully implemented and used alongside other control methods, the sterile insect technique could help countries reduce the numbers of mosquitoes and cope better with the diseases that these small but deadly creatures can spread. This report was produced by Louise Potterton for the United Nations.